All right, so let's talk about a particular phase change, vaporization, boiling. So, and this is kind of what's going on in a molecular level. So let's say that you had a completely empty container, stylized right here, and you magically, with, oh, I don't know, Star Trek transporter technology, beamed in a bit of liquid water, shown here. So what would happen is, at some point, some of these, there's an average energy for these guys. Some have more than the average, some have less. And it's quite possible that some that have more than the average energy, and that is near the surface, might actually have enough energy to break away from the hydrogen bonds that it has with its neighbors and release into the gas phase. And once that happens, it would do what gas phase molecules do. It would just kind of randomly move around until it either hits, until it hit another molecule or, the container. And maybe sometime later, another one undergoes this. And maybe 3. And maybe 4. Now, what would happen at that point is, while these things are randomly moving around, some of them might actually start to hit the surface of the liquid again, and they may or may not stay in the liquid. And at some point, the rate of escapes of water molecules from the liquid would equal the rate of recaptures from the gas into the liquid. And once that point is achieved, we say that these two phases are in equilibrium, that the relative amounts of both of them are the same. So, in these last two frames right here, there are 4 water molecules in the gas phase and umpteen of them in the liquid phase. Now, what you also need to understand is that any one water molecule is going to be going back and forth in between the liquid and gas phase, quite possibly a few billion times a second. But once equilibrium is reached, there's always going to be 4 of them in the gas phase and however many of them you've got in the liquid phase. And that ratio would not change until something else did, notably if you change the temperature. If you were to increase the temperature, you would get more of them in the gas phase because you have a higher average energy. And if you decrease the temperature for opposite reasons, you would get fewer of them in there. So this represents 2 phases being in equilibrium, in this case liquid and gas. The transition from one to the other, from the liquid to the gas, is called vaporization, or in colloquial English you call it boiling. And the opposite, going from the gas back into the liquid, is called condensation. So let's do this in math here. So equilibrium, we're going to talk a bit more about this in another chapter. This is a state where 2 different processes that essentially cancel each other out happen to occur at exactly equal rates. And usually talk about a process like this with some sort of double arrow like this. So I could express the equilibrium between liquid and gas with this double arrow saying that, well, liquid's going to gas, but at the same time, gas is going to liquid. But this actually is not quite right either. Usually chemists like equilibrium arrows to look like that. And so in one direction, the process is vaporization. In the other direction, we've got the condensation process going. What else do you need to know? So in any equilibrium, the reason why the relative amounts of the reactants and the products don't change is that both rates, forward and backwards, are exactly equal. And the other thing to know is that the gas produced by the evaporation, like all gases, well, they exert a pressure on the container walls and also on the liquid below it. Now, this pressure, or more specifically its magnitude, can actually tell us a bit about relative strengths of the intermolecular forces, just like we used the boiling point to a couple lessons ago. So here's an example.
And so this graph here, we're going to take a look at the effect of the strength of the intermolecular forces on the vapor pressure or something. And this will tell us why the boiling point is a good indicator of how strong they are. So these graphs look familiar. That's good, because they should. These are the graphs that we saw back last semester when we were studying the kinetic molecular theory of gases, and this is kind of the shape the curve the speed distributions took. So right now for this one we're going to focus on just one curve, let's say the blue one. And the energy needed for a molecule to escape from its neighbors, to go from the liquid state to the gaseous state, is a constant. And let's say that for a particular substance, that has low intermolecular forces, or weak ones, it's going to have a low enthalpy of vaporization. We'll say it's this number right here. And to compare it with, here, a compound that is exhibiting higher intermolecular forces, a higher enthalpy of vaporization. And that would be here. So the pressure that something is going to be exerting is going to be the part of this shaded area that is beyond that line. So clearly there's a much greater area beyond the red line than there is the blue line, and this indicates that a greater fraction of the molecules are going to have energy greater than this one than they do this one, by virtue of being at that particular temperature. And so this is why if you have stronger intermolecular forces, you've got a higher enthalpy of vaporization, which means a smaller fraction of the molecules can escape, which results in lower vapor pressure. So that's the trend you want to remember. Strong intermolecular forces, low vapor pressure. And with this graph here, we're going to compare why the pressure changes with temperature. So here again, we're going to compare both curves. And again, so this is the same compound at two temperatures. So we have one enthalpy of vaporization, one cutoff where the molecules have enough energy to escape their neighbors and become a gas. And remember how these curves change with temperature. The average shifts to a higher speed, higher energy, and they also broaden out quite a bit. So at the low temperature, the number of molecules that have enough energy to escape their neighbors is just the shaded blue area here. And at a higher temperature, T2, the number that have that sufficient energy is this entire orange shaded area, and actually the blue one, so it's this entire triangle shaped piece either, which is clearly much more. So at the higher temperature, a higher fraction of molecules have enough energy to escape. They will do so. You have more gas phase molecules, and so at a particular temperature, a compound, as the temperature goes up, the vapor pressure of the compound is going to go up, and this applies for anything.
So what I've got here in this graphic is this is showing you the vapor pressure exerted by three compounds, methane, CH4, methanol, CH3OH, and water, at a variety of different temperatures. This is in degrees Celsius. And for clarification, 1 atmosphere of pressure is sort of noted right here. So I want you to look at this graph, and you can look at it in a couple of ways. One of them is, what the temperature at which the vapor pressure of these various compounds will be at 1 atmosphere. How much energy does it take to get 1 atmosphere's worth of molecules into the gas phase? So think about that, and then tell me which one of these you think has the weakest intermolecular forces and which has the strongest intermolecular forces. All right, so the way that you want to think about this is the thermal energy needed to get 1 atmosphere's worth of methane molecules is a paltry, let's see, 120, 140, 160, about 165 degrees below 0 Celsius. So you do not need a whole lot of thermal energy to get 1 atmosphere's worth of methane molecules into the gas phase. Methanol, on the other hand, requires a temperature of, so this would be 40, 60, 80, let's call it 82 degrees Celsius. And water requires, doesn't get that pressure until 100 degrees Celsius. So the methane required by far the least temperature, the least amount of thermal energy to get that much, that many molecules in the gas phase. Water took the highest, and methanol is in the middle and much closer to water than it is to methane. So this is an experimental statement that, that the intermolecular forces here are stronger because you need a lot more energy to break them. Now, could we predicted this? Is this kind of what we expected based on what we know about intermolecular forces? Well, let's look at the Lewis diagram for these guys. So this is the Lewis diagram for methanol. I'm sorry, that's methanol. The other one was methane, and here is water. So this is, and now let's think about the intermolecular forces that are available to each. This is all CH bonds. They are not polar, so there is no way that molecule is polar, which tells us that that has only London dispersion forces available to it. Methanol, on the other hand, is a polar molecule because of this carbon-oxygen bond and this oxygen-hydrogen bond. And here I've actually drawn lone pairs on the oxygen. So like any molecule, this has London dispersion forces available to it. It's polar, so it also has dipole-dipole interactions, but more importantly, you have a hydrogen bonded to an oxygen. So this hydrogen bonds, and that is going to be the dominant intermolecular force for this molecule. Now, what about water here? It's actually the same situation. There are London dispersion forces. It's polar molecule because of the oxygen-hydrogen bond, so there are dipole-dipole interactions at work here. But it also hydrogen bonds. And when you've got hydrogen bonding, that's usually by far the most significant intermolecular force. And you can also imply that the hydrogen bonding is actually a little bit stronger in water because of the difference in the temperatures at which you get the 1 atmosphere. So it looks like of the 3, water has the strongest intermolecular forces. So that's one way you can look at it. You can look at the temperature at which a particular pressure is achieved. Now, you could have done half an atmosphere. You could have done 3 atmospheres and gotten the same ranking. Another way you can do this is by seeing what the vapor pressure of these molecules are at one particular temperature. So what you want to do in that case is look at a particular temperature, it doesn't really matter which one, where you've got where you've got data for both compounds here. Now, in this case, at, I don't know, 85 degrees Celsius, the vapor pressure of water is about, let's say, 0.65 atmospheres. And the vapor pressure of the methanol at that point is going to be about 2.4 atmospheres. So at a particular temperature, you've got a lot more of the methane molecules in the gas phase than you do in the water. And again, you can use that to imply that the intermolecular forces in methanol are weaker because than they are in water, because at a particular temperature there's way more of these guys in the gas phase than there are of this one. And since the vapor pressure of methane would be way off the scale in this case, you can infer there that those intermolecular forces are much weaker than what you've got in either one of these two. So you've got 2 ways you can look at it. The vapor pressure at the same temperature, in which case higher pressure, weaker intermolecular forces. Or you can look at the temperature at which a particular pressure is achieved. The higher the temperature to get to that pressure, the stronger the intermolecular forces are. So